All right, everyone. This is our final advanced data mining project, and this is by Trenbo, Parsa John Liu, and Landon Tompkins.
Okay, first up, we will go over the supervised learning with the decision tree, and we have given two dataset A and dataset B, and for each classification method, I use the test set and the cross-validation methods. So we first normalize the dataset, put it through the decision tree classification, and then apply the model and get out the performance. With the dataset A, I get the accuracy of 17%, and the reason why it's so low is because there are too many classes in the dataset A and too few sample to build the model. And the decision tree is not good in classification problem with many classes and small number of training sample. Okay. For dataset B, the accuracy is higher, 57%, but you can see in the bottom, the prediction is made totally for the Smurf class. The reason for this is the dataset B is the imbalance class where the number of sample in the Smurf class take more than 60% of the entire dataset. Move on to the native base. I set up the process the same with the decision tree. At the result, I get 44% accuracy, but the accuracy get higher. This is because the native base is a high bias and low variance classifier. It can build a good model even with a small data set like dataset A. For dataset B, the accuracy dropped down to 20% and all the prediction go into the normal class. The reason for this is I can tell you from the bottom, there are some values in the flat class in the training set that do not exist in the test set, and the classifier will return the 0 probability and will not be able to make the prediction. The next classification method is the random forest. For the dataset A, the accuracy we get is 18%, and the bias still toward the normal class, which is not a good thing. But for the dataset B, we get the accuracy of 97%. This is because the random forest can create many decision tree and is very good, make really good prediction for large and complex data set and dataset B. The last classification method is the SVM. For the SVM, we get the accuracy of 92% for dataset B, but the prediction is all belong to normal class. And the reason for this is data set A also an imbalance data set with 91% of the entire data belong to class normal. Data set B, the accuracy only 14. The SVM is not suitable for classification of large and imbalanced data set like data set B.
All right, next moving on to rule-based learning. We're going to start off with rule induction, and we use 10K folds for this one. At bottom left, you can see the training process that we use to train our data, which started with generating IDs, discretizing our data, then running it, and then converting it from numerical to binomial, then setting the rule, and lastly, using rule induction. On bottom right, you can see the testing process, which applied that model, and then we use a performance operator to get the accuracy. Moving on to the accuracy results, you can see that for each one of the data sets, starting from the top, which is data set A, resample 10 had a 96.28, the next one had a 92.44. Data set B, resample 10 had 100% accuracy, and data set B, resample 5 test set had a 60.95% accuracy. As far as FP growth goes, on bottom left, you can see the training process that we use, very similar to the previous one, setting the roles, numerical to binomial, then applying FP growth, and then rule induction. For testing this, we also did very similar, which was applying the model and then using the performance operator to get the accuracy. As far as the accuracy goes, we wanted to have varying support, which we have in here 0.99. We also implemented 0.95 and 0.90, which we'll show later. For the accuracy of 0.99 support, you can see that DARPA A resample 10 had a 93.83% accuracy. Next up, it was 91.55. And for DARPA and for dataset B, resample 10, we had a 98.39% accuracy. And lastly, we had a 96.44% accuracy. Moving on to support being 0.95, the first data set, DARPA A resample 10 had an accuracy of 96.28. Next one had a 92.44. Data set B resample 10 had 100% accuracy, and DARPA B resample 5 test set had a 98.78% accuracy. Lastly, when the support was 0.9 for FP growth, the results came out to be 97.38% for the first data set, which was DARPA A resample 10, 93.52 for DARPA A resample 5 test set, and 100% accuracy for DARPA B resample 10. And lastly, 99.62 for DARPA B resample 5 test set. Moving on to association rule generation, we wanted to generate some rules, which we'll show it in the next slide. The process for creating those rules started from retrieving that data, generating some IDs, selecting certain attributes. If there were any missing values, replacing them with the averages, converting the data from numerical to binomial, running it through FP growth, and then creating association rules using the operator that you can see in the slide. Here's an example of some of the association rules that were generated using the previous process that we explained. Lastly, there were some issues finding an a priori operator in RapidMiner, and looking into the internet, we were not able to find anything. Other students were also having the similar issues, so we decided to skip this one as we could not find the right resources for it.
Okay, the last machine learning methods we do is unsupervised learning. Started with that, I will go through the k-mean clustering. You can see right here, we retrieve the data, we set row, do nominal to numerical, do normalization, sampling, and then optimization. So optimize parameter to avoid the k-mean clustering, set a fixed value for k, and this can maximize the performance of the model. For the nominal to numerical, this helps the clustering with k-mean because since this method of clustering requires numerical value for it to calculate the distances between symbols. As you can see right here, data set A return k equal 41. We actually have 21 classes for data set A. For data set B, k equal 37, and actually only have three classes for data set B. The reason for the inaccuracy of both data set in clustering method is because the sample is too large, and the distance and the clustering method try to maximize the distances between cluster, and since the data is too large and the class is not very clear, that's why it get the error in class to cluster it. Moving on to DB-scan. The DB-scan is a density-based clustering algorithm, and all I do is I set the row, do nominal to numerical normalization, sampling, and then apply the DB-scan clustering method. For the first data set, we get 26 clusters, which is very close to the original number of classes in data set A. And you can see that cluster 0, it takes 50% of the data set, which is maybe the normal class in the data set A. And since the data set A is an imbalanced class, the rest of the cluster might not be accurate. Data set B, we got 40 cluster compared to what we're supposed to have, which is 3 classes. This is not very good model. And the reason for this is, again, data set B is a very inbound data set with a large number of sample and really small number of classes. And that's all for our presentation. Thank you for listening.